Hi, this is Professor Greg Smith, instructor for Cellular Biophysics and Modeling, a required course in the neuroscience program at the College of William and Mary. One of the students asked if I would review the concept of a half-center oscillator that has come up in our study of the neuronal-based rhythmicity in central pattern generators, and I'm going to do that here. As you see in this slide, one of the preparations that has been used in the study of central pattern generators is the stomatogastric ganglion of the lobster and crab, both of which are crustaceans. And on the left, you see kind of a diagram of the experimental preparation. In panel B, you see a diagrammatic representation of the various neurons involved in the central pattern generator, inhibitory synaptic coupling between them, as well as gap junctional coupling. And in panel C, you see rhythmic bursting of various neurons in this network, where it certainly appears that the phases of the timing of the active phases is correlated to one another in various ways. This is another example. So now when we're thinking about central pattern generators, a number of questions come to mind and that are sort of outlined here on this slide. And one of the most important things to ask is whether each neuron, if uncoupled, would be an intrinsic oscillator, or whether it would be a conditional oscillator. So what I mean by that is that if a neuron was not coupled to any other neurons, would it intrinsically burst? Would it alternate between silent and active phases? The silent phase being hyperpolarized and the active phase being depolarized, and action potential sort of riding on top of that plateau. And that's one of the most important things if you're trying to understand the function of coupled neurons. You need to know what the activity of a neuron would be in isolation, and this can be probed experimentally by blocking, using pharmacological techniques, the synaptic connections between neurons. The concept of a half-center oscillator was introduced a long time ago by Brown, and the idea here is that you can get two reciprocally coupled inhibitory neurons to fire synchronously but anti-phase from one another, so that one neuron's active and the other neuron's silent, and then they sort of exchange roles on a relatively quick time scale, and then the pattern sort of repeats. This the diagram here in the upper left is simply a representation of two neurons that are reciprocally inhibitory, and the activity of the red and blue neurons is represented down here below, and you can see that the symmetry in the response, each neuron sort of being active or silent in alternating succession as time goes on. Now, the way that this is best understood, at least a first approximation, is through Faceplate Analysis. And let me see, I'm going to switch to this one, I think. Through Faceplate Analysis, where what you do is make the assumption that the actual spiking that's occurring during the active phase isn't so important. It's simply the fact that when you're active, those action potentials are going to result in neurotransmitter release onto the neuron that is postsynaptic to the active neuron. So what I mean is that we're not going to model action potentials per se. We'll simply model the silent and the active phases of a neuron. And we know how to do this. We take the two-dimensional phase plane and graph two different null lines. This null line labeled free is meant to be the voltage null line for an isolated neuron. And then the green null line is the null line for a slow recovery variable. So if this were Morris car, the voltage null line would have a form that we've seen before, and the slow variable null line would represent the gating variable for the outward potassium current, the delayed rectifier potassium current. But we could even think of this more in a more idealized way. We just want to sort of know what the null line is for the fast variable that represents the transition between silent and active states of a neuron, and then we need to know the null line for the slow variable that will help us determine the transitions and the timing of the transitions between the active and the silent state. So what I'm going to do is remove this null line from the picture temporarily, and just think about one neuron in isolation and what would happen if the null lines were oriented in this fashion. And we're assuming here that the horizontal axis is voltage and the vertical axis is, say, W, the gating variable for the outward potassium current, the delayed rectifying potassium current. And if these were the null lines for our system and we knew that voltage was faster than W, then A would have to be on a stable branch of the voltage null line as it is now, and this null line would be appropriately labeled free, because if we're only thinking about neuron A in isolation, so just neuron A, not neuron B, and we're asking what is it going to do, we would just be using what's called the free null line, the null line that corresponds to A without the action of a neurotransmitter on its postsynaptic receptors. So what happens here, A would drift down the null line to this knee, and at this point, it's moving in this direction because the state of the system is trying to move to the point, the steady state value for the gating variable W, which is downward, but it needs to stay on the voltage null line because voltage is a fast variable. And when it gets to this point, it sort of leaves the knee, and now the only stable voltage for this value of W is over here. So there's a rapid increase in the membrane potential until you're at the depolarized branch of the voltage null line. And then as time goes on, at this, when the neuron's active, the gating variable that we sometimes refer to as W wants to increase. And in order to do that and stay on the voltage null line, A has to drift in this direction. And it will do so until it gets to this point, which is a stable fixed point of the dynamics for neuron A in isolation. And so you see that even though our initial condition was for A to be silent, A is ultimately active in this picture. So it would be tonically active, and A, you can think of A as spiking repetitively here. And so what the null lines are indicating is that neuron A in isolation is not a rhythmic burster. It's a tonically active neuron. Now, what we do is we add, in order to understand the neurons when coupled, is we add another null line, which is where the voltage null line sits when a postsynaptic neuron is inhibited by a presynaptic neuron. And then we have two neurons now, so I'll make another one here, labeled B, and we will position, because both neurons are identical, we can locate them both on this face plane. We just need to have a few things that are consistent with one another. For example, this would be a valid initial condition because what we're saying is neuron A is active. It's on the right side of the synaptic threshold, and neuron B is inactive. And if neuron A is active, then that means neuron B should be on the inhibited nuclein because it's receiving inhibition from neuron B. Because neuron B is receiving inhibition from neuron A. On the other hand, neuron A is on the free nuclein because neuron B is silent. It's not spiking, and so neuron A is not receiving inhibition from neuron B, and that's why it's on the free nuclein. Now, this is a valid initial configuration, but what would happen next is neuron B would move down the inhibited nuclein until it gets to the knee, in which case it would jump to across the synaptic threshold, and it would be moving towards this inhibited nuclein, and you can think of it as stopping here. But now neuron B is active, and that means neuron A has to move to the inhibited nuclein. And notice that in order to do that with a horizontal direction of motion, A needs to move in this direction to the inhibited nuclein branch. It's hyperpolarized here, so now neuron A is silent and neuron B is active. But if neuron A is silent, neuron B is not being inhibited, so it will move to the free nuclein in a horizontal fashion. Right? So those motions, you can think of them as happening relatively quickly, and now the slow evolution will occur again, and neuron A will gradually be moving in this direction, whilst neuron B moves like this. And let's say that A gets to this knee a little bit before A gets to the steady state up here. It doesn't really matter that much. And at this point, neuron A will become active, and it will jump to the inhibited nuclein here, which causes B, since neuron A is active, B has to move to the inhibited nuclein, which it can do so in this way. But now neuron B is not active, and so it should be on the free nuclein. So you can see that right there, A and B in that last sort of argument during one phase of B being active and A being silent, we're now in a similar situation where A is active and B is silent. So this process will repeat. And this is an example of a half-center oscillator. It is a half-center oscillator because the neurons, A and B, when uncoupled, are tonically active. They're not oscillatory, but when coupled, if this is the proper arrangement of nucleins, meaning if we position the inhibited nuclein in the right way here, then when coupled, our analysis of the phase plane suggests that these neurons will be anti-phase. They'll be in synchrony, but in an anti-phase fashion. So one neuron will be active, the other neuron will be silent, and then they'll exchange places, and that process will continue indefinitely. So that is an example of a half-center oscillator. And the last thing to say here is that if you think about like really why is this happening, an important point was that even though A might be tonically active on the free nuclein while B is silent, B, right, the dynamics of B here allow B to go underneath this knee and escape the inhibition of A. And it's this escape from the inhibition of A that actually allows the two neurons to trade places. And so this mechanism for a half-center oscillator is referred to as an escape mechanism because neuron B actually becomes active. It leaves the silent phase and becomes active whilst the neuron A is providing inhibition. So B has been able to escape the inhibition of neuron A. So this is referred to as an escape mechanism. The alternative would be if neuron A nuclein looked like this and neuron B's looked like this. B would get stuck down here. Neuron A, when active, would move over this nuclein and drop down. And it would actually be the timing out of the active phase of neuron A that caused neuron B to become active. And that mechanism is refer to as